if all they could use was demographic information, and then sort of moving to the top left, you can see that if in fact they had full information for sort of all the choice information that is in the data set, they would be able to infer much more precisely for each household how price sensitive they were. And obviously that would be very valuable for tailoring these coupon values to the households. Okay, let me look at a second example. So this is based on a paper by Gary Chamberlain and Kei Hirano. They were interested in deriving predictive distributions for earnings using panel data. And so they had a linear panel data model where log earnings is linearly related to some covariates. Then there's an autoregressive component in this model, VIT here. There's an individual specific permanent component, alpha I. And then there's the idiosyncratic component UIT that is independent over time and as well as across the individuals. So the VIT follows the first order the regressive process there with the common parameter. With the initial condition coming from a normal distribution, the initial value coming from a normal distribution, and the increment coming from a normal distribution. And the key difference between this model and sort of a lot of the models that have been used in this setting is that they allow for an individual specific variance. So this HI here, so the idiosyncratic, the last term in the log earnings model has a standard normal component multiplied by 1 over h. So where 1 over h is the standard deviation. And so trying to estimate sort of both the individual specific component, the additive individual specific component alpha I and HI directly, clearly wouldn't work with sort of the standard frequentist argument would be that for fixed t, with the number of observations going to infinity, you wouldn't be able to estimate those consistently. From a Bayesian perspective, in some sense the problem is that using a flat prior distribution on a very high dimensional parameter space doesn't really work very well. And so analogously to this hierarchical model that Rossi, McCulloch, and Allenby use, Chamberlain and Hirano use a random effects or hierarchical model, where these alphas are viewed as coming from a normal distribution and the h's are viewed as coming from a gamma distribution. And so now instead of directly trying to estimate these parameters, they go to use specified prior distributions on the sigma alpha squared, as well as the parameters of the gamma distribution m and tau. But the hope and the presumption that by now having a model with relatively few parameters, the prior distribution is going to be much less important, and so that's very likely to work well here. Just having a couple of parameters with a large amount of data is going to give you results that are fairly insensitive to the choices of these prior distributions. And so using data from the PSID, so the main thing I want to show from this paper, and this is just a table taken from that paper, they find that there's a lot of evidence that there's heterogeneity in these variances. And so there's a lot of these, the standard models assume that the variance is the same for all individuals. They find that there's actually considerable variation in this considerable dispersion in the distribution of age. So here, in terms of the conditional standard deviation of that term, you see that 0.1 quantile for this standard deviation of log earnings is 0.05, and the 0.9 quantile is 0.45 if you average it over all individuals. Again, more specifically, they want to actually look at predictive distribution at the individual level. And so they're taking two particular individuals, one who had a relatively large amount of variation in their log earnings, sort of after taking out these the other components, and one who had a relatively low amount of variation, so with the sample standard deviation of the residuals 0.07 versus 0.47. What this model shows you is that even 5 years later, there's much more dispersion in the earnings distribution for the second individual, for the individual with a lot of variation early on, than for the individual with very little variation in their earnings early on. It's sort of clear that this for various policies or for individual behavior, this may very well be very important. Okay, let me do a couple more examples. So this is from an early version actually of a paper that I wrote with Gary Chamberlain, where we're looking at the many instrument problem from a Bayesian perspective. And so the way we set it up there is we looked at the reduced form for years of education. So this is applying this to the Angress-Kruger problem. We look at a case where we had a potentially large number of instruments. So we have a linear reduced form for years of education as a function of all the instruments, and a linear reduced form for log earnings with the parameter beta multiplying the reduced form of education. So beta is the return to education here, the parameter of interest. Assuming joint normality for the reduced form disturbances, you get a likelihood function. So now we have a fully parametric model. We get a likelihood function that we can try to use either by doing maximum likelihood estimation or by using some Bayesian procedure. And so the key here, and so the focus of that paper was that if we're interested in beta, we may be concerned about the sensitivity of those inferences to the choice of the prior distribution, in particular with respect to the use of so many instruments. And so one way to think about why that could be a problem is to think not just in terms of the prior distribution on pi 1, but to think about the prior distribution on the sum of the squared pi's. In some sense, the sum of the squared pi's measures the total amount of information that is in the instruments. If we're concerned about weak instruments, we are concerned about the possibility that all the pi's are equal to 0 or close to 0. And so we're in fact concerned with the possibility that the sum of the squares of the pi's is close to 0. And now, if we use a flat prior on a large number of these pi's, if we use a flat prior on pi 1 in a setting where we have a large number of instruments, then essentially the implication of that is that we put all the prior probability mass on the sum of the pi squareds being fairly large. So if we say that the probability that any of these pi's, well, sorry, if we choose a prior that is very dispersed, that puts a lot of mass on, so that is very flat in a large part of the parameter space, the implied prior distribution on the sum of the pi squareds is necessarily putting necessarily very little mass on the area around 0, which is actually the area where we're most concerned with. And so if you're concerned with the parameters being in a particular area of the parameter space, you clearly want to avoid using a prior distribution that rules out that area. And so what we then show is that if you actually do that, if you choose a flat prior distribution for pi 1, you get pretty much two-stage least squares back. So in some sense, so the flip side of that is that you can interpret the two-stage least squares estimator as pretty much the same as using a Bayesian approach, where you use a very unattractive prior on the first stage, namely a flat prior on the first stage. And so what we then did is use an alternative prior distribution on the pi's, where we assume that each of the reduced form coefficients came from a normal distribution with some common mean and common variance. And so that now we've reduced the problem to choosing a prior for mu pi and sigma squared pi. That's a very small, low-dimensional parameter space. There it's very easy to think about what are prior distributions that are relatively uninformative. And then what you actually find in the data is that most of the posterior mass is concentrated on very small values of sigma pi squared, which makes perfect sense. You know that the true values for these pi's all have to be pretty small. They don't necessarily all have to be equal to 0, but you in fact have pretty strong substantive prior reason to believe that all these reduced form coefficients should be fairly small. And ignoring that by using methods that sort of treat these pi's as being completely unrelated and possibly being extremely large is in this case a very wasteful way of using the data, and one that is that turns out to be extremely misleading. Okay, let me do one more. In some sense, that's sort of very substantive example here. This is a paper by Gewicki, Risan, Karan, and Town. We're interested in estimating the effect of hospital quality on mortality. And so, obviously, you don't want to just compare mortality, sort of raw mortality rates by hospital, because there's considerable reason for concern that more sick patients would go to better hospitals, or at least would try to go to better hospitals, and that as a result, good hospitals may have relatively high mortality rates just because they get sicker patients. So the way these authors set this up is they set up a linear model for latent mortality that depends on the hospital you go to, as well as on individual characteristics. Then in addition, they model hospital choice as a discrete choice problem, but now, just as in much of the current I/O literature, there's a large number of choices. So they model this through a latent utility setup, where the utility associated with going to hospital J is linear in the characteristics of that hospital, sort of possibly interactive with some individual characteristics, and the potential patients then choose the hospital that has the highest utility for them, sort of given their characteristics. And so the way they model the endogeneity here is that they allow for correlation between the unobserved preferences for the hospital, the eta ij's, as well as the unobserved individual mortality, epsilon I, through this linear relation, where the epsilon I is linearly related to all the eta ij's with hospital-specific coefficients delta j. And so then sort of this is obviously again a case where you have a fairly large number of parameters trying to figure out what the likelihood function looks like evaluating the likelihood function would be extremely difficult. In principle, this would be possible using simulation methods. In practice, this would be infeasible. But setting this up from a Bayesian perspective and using these Markov chain Monte Carlo methods is actually going to make it fairly straightforward to get draws for all the parameters of interest and for doing any policy experiment that you might want to do in this case. And so what they so again, the log likelihood function in this case would be highly nonlinear. Frequentist methods in the end would require that it sort of be well approximated by a quadratic function, which is clearly not going to be the case here. It's going to be multimodal, and so that's part of their motivation for using Bayesian methods here as well as computational. That it's just going to be much easier. And so in their empirical analysis, they actually find that this works very well. They find strong evidence that the selection into the hospital is non-random, and sort of do a variety of other things. Okay, let me do the last example. This is on some recent work I did with Susan. So we were interested in discrete choice models, sort of in these somewhat related to the Rossi-McCallum-Allenby settings, but sort of more closely related in a sense to the Berry, Levinson, Pecos setup, but in contrast to that study using individual level data. And we were interested in allowing for possibly multiple unobserved choice characteristics. So we did some theoretical work showing that in principle, in order to be consistent with observed choice data, you may need more than one unobserved choice characteristic. Once you allow for that, it's going to be extremely hard to do maximum likelihood estimation. You again end up with a likelihood function that is going to be multimodal, and so any approximation that is fundamentally based on a unimodal likelihood function that is approximately quadratic is going to be very inaccurate. And so what we did instead is set it up from a Bayesian perspective, sort of using the sort of pretty much the same latent utility setup that these earlier papers used, allowing the utility to depend on choice-specific characteristics with individual-specific parameters, then allowing for unobserved choice characteristics with individual-specific parameters, as well as some idiosyncratic error term, and then modeling the individual-specific parameters as coming from a normal distribution centered at a linear combination of individual characteristics with some variance. And then, sort of even though in principle this would be very hard, would again be very hard to set up to calculate the likelihood function, setting up a Markov chain Monte Carlo algorithm to get draws from the posterior distribution is conceptually very straightforward. You break it up in lots of different parts where you observe conditional on various unobserved latent variables, and with all the steps being at least conceptually straightforward. And so, there'd been earlier work where people had used multiple unobserved choice characteristics. In particular, some work by Elrod and Keene and Gutler and Shekhar. So talking to, we presented this at some point with Mike Keene in the audience, and he was very much in agreement with. Sort of his point was that had he known about those Bayesian methods at that time, which was the time really they were being developed, he would have used those for that paper as well, because it seemed a much more sensible method to him, because with what they did, the computational burden was very heavy. Okay, any questions here? Yes? Yeah, I mean, actually the first comment. Let me first make a comment on the first thing you said. I think it's sort of more the perceived computational difficulties. I think nowadays these methods are actually just much simpler. In addition, a lot of these Bayesian computational methods have actually been implemented in packages. There's several of those packages around. I don't actually have that much experience with any of them, but there's a software package called Bugs that does a lot of this. There's actually got an email from Peter Rossi the other day saying a lot of the models he's implemented, he's made software available for, but that's in R, and some. I suggested he write it in Stata, and he said no. But so if you want to use R, which is actually freely available, but then maybe, but then you can use a lot of these things very directly. Actually, on the same vein, someone asked earlier about some of the software for the things we talked about yesterday. And so for some of the evaluation stuff, there is some Stata software available. There's some references on my Harvard website, so you can look some of them up there. But then, sort of getting back here, so there's a lot of theoretical work on how well these Markov chain Monte Carlo methods work. That doesn't seem to capture quite how well they work. So it turns out that in practice they just work phenomenally well, much better than you would have reason to expect, and so. So in most of these models, they just pretty much, I mean, you clearly want to start somewhere where you think the parameters are, but unless models are very extremely nonlinear and irregular, these things tend to converge very fast and work very well. And so, I mean, I'm not quite sure. So in the notes, there's a bunch of references to that literature. So one of the most readable introductions to that literature, and actually from a more econometric point of view, is a 2004 book by Tony Lancaster, where he also kind of gives some links to some of the software. But it just turns out in practice these things work extremely well, and so there's a lot of things you might expect could go wrong, but it's very rare that these things actually do go wrong in practice. Yes?
Follow up on that. So I'm trying to understand whether you simply have a better calculator for doing adding up numbers rather than doing it in your head, so it's just computationally better, or whether you're imposing some structure on the model that gives the results, and if so, how important is it?
No, I think sort of fundamentally these methods do the calculations more efficiently by evaluating the probabilities sort of in the right area. So what do I mean by that? So if you look at sort of frequent assimilation methods for these discrete response models, you need to do this at lots of different values of the parameters, including some that are far away from the truth, that are in the end irrelevant, where these probabilities may be hard to estimate because they're very close to zero, and so taking logs could lead to a lot of variation. These Bayesian methods move around sort of in the end, given that the draws correspond to draws from the posterior distribution, they tend to be in the area around the true parameter values. And so they're much more efficient in that sense. They don't waste a lot of draws on the irrelevant parts of the parameter space. And so there's some work. So I'm trying to think actually what the exact reference is, but there was this literature in the 90s looking at simulation methods for the discrete response models, and so there were some work by Guido, Facilio, Keen, and in the end, I think their eventual conclusion was that Gibbs sampling was better than the frequentist simulators they developed. I think there's a review of economics and statistics paper with Guido and Keen among the authors that makes that point in the end. Yes. Yeah, so I mean, if...
So in some sense, if we really want to appeal to Bayesian models, so the results have to be somehow independent of or not very sensitive to prior, which could be true when there is multimodality, but wouldn't be true when there are flat proportions of the likelihood function.
Yeah, I mean, in the end, if the likelihood function is flat over a large, important part of the parameter space, then it means we cannot say much. So that no matter what methods we use. On the other hand, if the likelihood function sort of has multiple modes, so that at that point, frequentist methods are going to have a lot of trouble because sort of the standard thing would be to use a quadratic approximation to the log likelihood function, and that's not going to fit very well. And sort of none of the methods. So none of the non-normal approximations tend to be particularly helpful. And so in that case, Bayesian methods I think are very useful. But in the end, it's sort of clear that that good practice would be to report these things and report the sensitivity to the prior distribution, and that's not all that difficult. Now, sort of. On this paper with Susan, actually, one of the editor complained that, well, but these Bayesians, they never actually report the sensitivity to the prior distribution. In some sense, that's not so different from the fact that almost never do people report evidence on the quality of normal approximations. And it really, that is pretty much the same thing. Now, that doesn't excuse the other part. I mean, it clearly is important to report sensitivity to the prior distribution. And I mean, I'm not saying that sort of being very formal about a Bayesian perspective is clearly useful in all settings. Sort of I've had this discussion a couple of times with Mansky about what the FDA should do, whether they should sort of view drug approval as a Bayesian decision problem, and it clearly doesn't seem very sensible to allow the introduction there of prior distributions. But I think that's because that's a much more complicated problem where there's sort of a repeated game between drug companies and the FDA, where drug companies are trying to use the rules to their to maximize profit subject to whatever the rules are, and allowing the introduction there of subjective knowledge could make that much more complicated. But in a lot of other cases, I think it's very clear, sort of in these cases with relatively low dimensional parameter spaces, having a flat prior is typically a reasonable starting point, and combined with some evidence of the amount or the lack of sensitivity to that choice, I think it's a very sensible thing to do.